Welcome everyone. In this video, I'll be going through the solution to question 324 from the list of sample exam P problems on the SOA website. The question reads, an actuary determines that the daily auto accident count within a city can be modeled by a Poisson random variable to mean 4. So I'm going to denote that variable x. So x, number of accidents that occur in a day in that city is Poisson with a mean of 4. In addition, the accident count on different days are mutually independent. They want us to calculate the approximate probability that at least 6,496 accidents occur during a period of 1600 days. So I'm going to define a new variable, t, and I'm going to let that be the total number of accidents that occur over 1600 days. So t represents the number of accidents over a 1600 day period. I want to calculate the probability that at least 6,496 accidents occur over that time period. So t is going to be greater than or equal to 6,496. So t then is simply as I said before, it is the number of accidents over 1600 days. And remember that x represents the number of accidents per day in that city. So t would simply be the summation of 1600 of each of these variables. So it will be x1 plus write some ellipses there, x is 1600. So we need to find the expected value of t. First of all, this is a central limit theorem problem. The reason it's a central limit theorem problem is because of how huge the sample size is. We're talking about 1600 random variables, and whenever it is the case that we have such a huge number of random variables, then we're going to very much closely approximate the normal distribution. So t, of course, is going to be normally distributed. So we need to find the expected value of t, and we need to find the variance of t. So the expected value of t is equal to the expected value of x1 plus the expected value of t x1 plus, I'm going to write my ellipses there again, the expected value of x 1600, and this is simply going to be equal to 1600 multiplied by, remember that the variables are independent and identically distributed, so the means are very much the same. So that is simply just 1600 multiplied by 4, and this should give us, I think, 6,400. Let me plug that in my calculator real quick and see what I get. Right, so it should be 6,400. 6,400. So we have the expected value of t. Now we need to calculate the variance of t. The variance of t is equal to the variance of x1 plus x 1600. We're summing 1600 independent and identically distributed random variables. So this is equal to the variance of x1. So we break them up. We're going to break it up like this. Variance of up to the variance of 1600, x 1600, 16 up to the 1600 variable, and this is equal to So for a Poisson random variable, remember that the expected value is the same as the variance. So the variance of x is the same as its mean. So the variance is 4, and we have 1600 of these that we're summing together, which is just pretty much the same as saying 1600 multiplied by 4, and that again is going to give me 6400. Alright, so let me get some more space down here. So therefore t is normally distributed with a mean of 6400 and a variance of 6400. So now we're ready to find the probability that t is at least 6496. 6496. So we just need to standardize this thing now. So we have p, z is greater than or equal to 6496 minus the mean of t, which is 6400, over the standard deviation. So standard deviation, that's simply the square root of the variance, and that should give me, I think, 80. So I'm going to have 80 here. So we have z is greater than or equal to 6496 minus 6400 divided by 80, and that should give me 1.2. I'm going to have 1.2 here. So I always like to do a sketch. So we have 1.2 over here, and the probability that I want to find should be on this side. What is greater than 1.2? Alright, so that my z-score is at the bottom. I want to find the probability that z is greater than 1.2. So we want this area, we want that region. Now, in order for me to get this, I'm going to have to say 1 minus phi of 1.2. So phi of 1.2, that will give me the cumulative probability up to 1.2. So it will pretty much just give me this region. It will give me that region, and I'm going to subtract that probability from the overall amount of 1 to get what is remaining here. Alright, so let me look for phi of 1.2 on my standard normal table. So 1.2 is 0.88 0.88493. So I have here 0.88493. 0.88493, take so 1 minus 0.88493, and that should give me 0.11507. Let us check our answers, and that rounded to 2 decimal place is 0.12, which is of course our answer B. Alright, if there are any questions, feel free to post them.